Welcome. In this video, we are going to reevaluate this indefinite integral. If you're following along in my Canvas course as one of my students, you've already seen this. We covered this during our module on trigonometric substitutions. And we are going to redo this integral using at least two different computer algebra systems and then compare the solution obtained with these two cases with our manual solution. And then I have this follow-up question here. Was our manual solution incorrect? And I put that out there on purpose because a lot of times when you're using these computer algebra systems, you're going to get something that just looks weird or strange or doesn't make sense or correspond to the technique you are learning in your class, and you're thinking, am I not getting this? Am I getting this wrong? And it's a really important skill to be able to translate, say, one mathematical expression into different looking expressions that are all equivalent. So that said, open up a web browser. And on that web browser, you're going to want to go to geogebra.org and then in a separate tab, Wolfram Alpha. And so here at geogebra.org, click on this little grid here and go to Classic. And then once you're in Classic, click on these three bars and go to View, click on CAS, uncheck Algebra and Graphics. And so all we need is CAS. And in our CAS, you're going to type in 1 divided by the square root. So SQRT is generally what you use to type square root. And within that, go ahead and put x squared plus 2x plus 5. And then once you've entered that, tap it again and go integral. And there it is. GeoGebra evaluated this indefinite integral as this expression here. Now let's go ahead and go here to Wolfram Alpha. And we're going to do the same thing. So type in integral and then type in 1 divided by square root. And of course, this is not going to format as nicely for you since this is all text entry. So square root x squared. You can leave spaces, and I often do just to make it visually easier for me to see what I am typing. So x squared plus 2x plus 5. Close that parentheses and type in dx. And here is yet a different solution. And again, those of you following along with my course should notice that this looks nothing like what we got in our module on trigonometric substitutions. And you should also notice that this looks really deceptively similar, but not identical to what we got on our module on trigonometric substitutions. And then here, finally, you'll see the solution we obtained when we manually integrated this using a trigonometric substitution. Here is the expression obtained using GeoGebra. And then here's the expression obtained using Wolfram Alpha. What we're going to show next is that all of these solutions are in fact correct. And we're going to use some identities and also a lot of Ninja algebra to show this. Okay, so let's reconcile both of these solutions with what we computed manually in the previous module. And let's begin with this solution from Wolfram Alpha. So in order to make sense of this solution, you need the identity hyperbolic sine inverse of w is equal to the natural log of w plus the square root of w squared plus 1. So let's rewrite this solution here. So hyperbolic sine inverse of x plus 1 over 2 is equal to the natural log of x plus 1 over 2 plus the square root of x plus 1 over 2 quantity squared plus 1. And of course our constant, let's say plus c1. Continuing, we have the natural log of x plus 1 over 2 plus the square root of x plus 1 quantity squared over 4. And then rather than rewrite this as a 1 and have to take an extra step, 1 is the same thing as 4 over 4. And that'll help me add these fractions inside of the root immediately. So this is the natural log of x plus 1 over 2 plus square root of x plus 1 quantity squared plus 4 divided by 4 plus our constant. So as you can see, I have just rewritten things to make more space, and we're going to continue to simplify this. And we're going to use the fact that we can split up a square root, so that is a fraction inside a square root, into the square root in the numerator and the square root in the denominator. So let's take care of that. This is the natural log of x plus 1 over 2 plus, In our numerator, I have the square root of x plus 1 quantity squared plus 4. And in my denominator, I'm just going to have the square root of 4, which is 2, plus our constant. So now I can add these two fractions together. That is, get the natural log of x plus 1 plus the square root of x plus 1 quantity squared plus 4, all divided by 2, plus our constant. Now we're going to take advantage of the fact that if I have a fraction inside a natural log, I can rewrite this as the difference of natural logs, where the numerator is in the first natural log and the denominator is in the second one. Now I can say c is equal to c1 minus ln of 2, and then I can rewrite this one last time as the natural log of x plus 1 plus, and in my square root, recall that x plus 1 squared plus 4 is the same thing as x squared plus 2x plus 5, plus a constant c. Now, as you can see, we have reconciled this solution from Wolfram Alpha to match ours that we worked out manually. Okay, so now let's reconcile this solution here that we got using GeoGebra and ensure it's actually the correct solution. Here's a hint, it is. It just looks a little bit different, so let's work that out. So recall, if you have ln and you have, say, a constant up front, you can rewrite this as the natural log of whatever is inside, so the argument, to the constant power, so in this case to the a power. We have a negative out front, so let's write all this to the negative 1 power. That is, this is the same thing as the natural log of negative x minus 1 plus the square root of x squared plus 2x plus 5 to the negative 1 power, plus our constant c1. Rewriting further, I get, and as you can see from this step to this step, all that happened is I rewrote this negative exponent by moving it to the denominator of fraction. So now this may as well be to the 1 power. And I also factored out a negative 1 that these have in common. Now, I'm going to do this as an aside. That is 1 over negative x plus 1 plus the root of x squared plus 2x plus 5. I'm going to multiply this by its conjugate. And to make it a little more clear of what this will look like, I rewrote the denominator here to make it really obvious that we can just multiply by root x squared plus 2x plus 5 plus x plus 1 divided by the same quantity. Squared. Multiplying this out gives us this polynomial here, and then you should already be noticing that I'm going to have a positive x squared and a negative x squared, a positive 2x and a negative 2x, and then positive 5 minus 1. This will leave me with, okay, so let's put all of this in here. Okay, so let's take advantage of the fact, again, that the natural log of a quotient can be rewritten as a difference, as you see here. And then we can say, let c equal c1 minus the natural log of 4. And then this will match our original solution exactly. So as you can see here, what we worked out manually is equivalent to what we ended up with in the GeoGebra CAS. So a big takeaway I want you to get from this video is that when you're using computer algebra systems to evaluate integrals, your solution may not always look like something you've anticipated or may not look like something you already have in front of you. And that doesn't matter. That doesn't mean you're incorrect and you should rewrite your work. What matters is that you understand that equivalent solutions that are all correct, that are all antiderivatives of this function here, can just look differently. I hope this video has been helpful.